Hello everyone. In today's lecture, we will move to a new chapter, which is the Laplace transform. In the previous chapter, we learned about the time domain representation of LTI systems, and we've seen that if we have a linear time invariant system, the output from such a system is equal to the convolution between the input and the impulse response. And this applies for continuous time as well as discrete time systems. In this chapter, the new chapter, the Laplace transform, it will be a tool which we will learn, and this tool will help us to deal with LTI systems, but now in a different domain. We will call it the S domain or the Laplace domain. So, the Laplace transform is used mainly to represent continuous time signals and continuous time systems, and to find the relation between the system input and the system output in the new domain, the S domain. And this is done by expressing or representing the continuous time signals by using continuous time complex exponentials. This complex exponential will take the form e to the power st, where s is a complex variable. So here in this chapter, we're basically trying to represent any signal we have in terms of a complex exponential of the form e to the power st, where s is a complex number. It's usually denoted as sigma plus j omega, where omega is a frequency we have seen before, 2 pi f, and s is usually called the complex frequency. So in this chapter, we will be trying to represent continuous time signals in terms of complex exponentials e to the power st. And we have a similar tool that would be used with discrete time signals and discrete time systems, and this tool is called the Z transform. You will learn about Z transform in different courses, but in this course we will only learn about the Laplace transform. So again, the Laplace transform is used to represent continuous time signals by using a continuous time exponential e to the power st. There are two types of Laplace transform: unilateral Laplace transform or one-sided Laplace transform, which is suitable for solving differential equations with initial conditions. Mainly, when computing the unilateral Laplace transform, the integration is performed over time, starting at 0 up to infinity. So only we're taking the right half of the time axis from 0 up to infinity. That's why it's called unilateral or one-sided. Whereas in the bilateral or two-sided Laplace transform, which is more suitable to give us insights into the nature of continuous time systems, their causality, stability, and frequency response, we do the integration with respect to time from minus infinity to positive infinity, so you're covering the entire time axis. The Laplace transform actually plays an essential role in the design of continuous time systems in terms of determining the system properties like causality, stability, and position of poles will determine the frequency response of systems and so on. And the primary rule of Laplace transform is the transient instability analysis of causal LTI systems, which are described by differential equations. So first, let's define a complex variable s, where the complex variable s is equal to sigma plus j omega. Omega is the natural frequency we have seen before, which is 2 pi f, and now s is a complex variable we refer to as the complex frequency, where sigma is a damping factor and omega is a frequency. So why we are calling sigma as a damping factor? Let's move to our whiteboard over here. So we are trying to represent any continuous time signal in terms of the complex exponential e to the power st. So replacing s by sigma plus j omega, we will get e to the power sigma t times e to the power j omega t. And e to the power j omega t can be expanded using Euler's equation as cosine omega t plus j sine omega t. So as you can see, this term represents kind of oscillating functions, cosine and sine, whereas this term e to the power sigma t will result in sort of a decaying exponential, especially if sigma is less than 0. So going back over here, as you can see, we can write e to the power st as e to the power sigma t times cosine plus j e to the power sigma t times sine. If we try to plot the real part over here, which is e to the power sigma t cosine omega t, here is the cosine, the oscillating function. It's multiplied by a decaying exponential e to the power sigma t, so we'll be having a decaying kind of cosine. And for the imaginary part, it's a sine wave, so it's sinusoidal wave, sine wave with a decaying exponential as well. Why do we want to represent any continuous time signal in terms of e to the power st? In order to understand this, let's try to answer this question. Consider applying an input x of t, which is equal to e to the power st, to an LTI system whose impulse response is h of t. And let's try to find the system output in this case. So let's move to our whiteboard over here, and let's say we have a linear time invariant system whose impulse response is h of t. And now we have an input signal applied, x of t, where this input signal is equal to e to the power st. And now we need to find the output, y of t. Since we have a linear time invariant system, we can compute the output y of t using the convolution integral. So basically it's x of t convolution with h of t. So how can we perform the convolution? It's simple. So y of t is equal to integration from minus infinity up to infinity, and now we can take one signal, keep it as is, and the other signal will do a mirror and shift. Let's keep h of t as is, so I'll make it h of tau, and then x of t minus tau, and let's do the integration with respect to tau. So this will be equal to integration from minus infinity to positive infinity, h of tau times. Now x of t is equal to e to the power st, which makes x of t minus tau e to the power st minus tau. So we'll be having e to the power st minus tau d tau. So now this complex exponential can be divided into two parts, e to the power st times e to the power minus s tau. And of course, e to the power st can be moved outside the integration because we are integrating with respect to a variable tau. So moving on, now y of t is equal to e to the power st times the integration from minus infinity to plus infinity, and inside the integration we'll be having h of tau e to the minus s tau d tau. So again, what we did was simply that we expanded this e to the power st minus tau into two terms, e to the power st, which is considered to be constant with respect to tau, so we moved it outside the integration, and now we'll be having h of tau times e to the power minus s tau d tau. And in this case, as you can see, the output is simply e to the power st multiplied by this function, integration from minus infinity to positive infinity, h of tau e to the negative s tau d tau. This integration is actually depending on the function h. That's why we will call it capital H. And it will only be a function of s, because when you integrate with respect to tau and put the limits, tau will disappear, sort of, and you will get y of t equal to e to the power st times h of s. So let's revisit the problem one more time. We have an input e to the power st, and the output y of t right now is equal to e to the power st, which is exactly the same as the input, times h of s. So now that we have e to the power st exactly the same as the input, so the output y of t, which is function of time, is exactly the same as the input multiplied by h of s. And of course h of s, it's a function of the variable s, but it's considered to be a constant with respect to time. So h of s is a constant with respect to time t. That's why, looking at this equation, we can see that applying e to the power st to an LTI system, the output will be exactly the same as the input, e to the power st, of the same shape, same function of time, only multiplied by a constant h of s, and this constant is not changing with time. It's basically a constant with respect to time. And whenever we have this kind of configuration, when you apply an input to a system and you get the same input appearing at the output, we call this input an eigenfunction. So e to the power st is called an eigenfunction of the LTI system. Eigenfunction of the LTI system. And eigenfunction simply means that whenever we apply this kind of function to the system as an input, the output will be exactly the same function, same shape, same everything, only multiplied by a constant. And this constant, h of s, we will call it the corresponding eigenvalue. The corresponding eigenvalue. And also h of s, as we're going to see in few seconds, h of s, which is the integration from minus infinity to positive infinity, h of tau e to the negative s tau d tau, it is basically the Laplace transform of the impulse response. It's the Laplace transform of h of t. And h of t is the impulse response of the system. So its Laplace transform, we call it the system transfer function or the system function. So h of s is also called the system function or system transfer function. So in order to summarize what we have said so far, if we have an LTI system whose impulse response is h of t, and if we apply an input signal x of t, which is equal to e to the power st, the output y of t will take the form e to the power st, which is exactly the same as the input, multiplied by a constant h of s. And again, h of s is a constant with respect to time, where h of s can be computed using this integral, which is the Laplace transform of the impulse response h of t. And this observation or this property will make it much more easier to deal with LTI systems. So how is that? Let's imagine we have an input signal x of t, and somehow we managed to express it as follows. Let's say a constant a1 times e to the power s1t plus another constant a2 times e to the power s2t plus a third constant times e to the power s3t. And let's say we want to compute the output. We will apply this x of t as an input signal to an LTI system, and we need to find the output. Based on what we have learned in the previous chapter, we will need to do convolution between this input x of t and the system impulse response. But now, since we have learned that e to the power st is an eigenfunction of the system, we know that if we have an input e to the power s1t, the output will simply be e to the power s1t of the same form, but multiplied by a constant which is h of s. But now we have three of these terms added together. Now we can employ the property of linearity. Since the system is known to be linear, we can apply each individual component of the input individually and then compute its corresponding output and then add all the outputs together. So basically y of t will be equal to, due to linearity, we can start dealing with each term of those separately. So a1 times e to the power s1t will result in an output of this form. a1 is a constant. So e to the power s1t will result in e to the power s1t times h of s1. So we'll be having e to the power s1t times h evaluated at s1 plus the second term we have over here, a2 e to the power s2t will give us a2 e to the power s2t times h of s2, and same for the third term. So as you can see, now dealing with LTI system is very easy compared to what we have been doing previously using convolution. So the third term, this term, will give us a3 e to the power s3t times h of s3. So now, as you can see, dealing with LTI systems has become really easy because e to the power st is an eigenfunction of LTI systems. Again, when you apply e to the power st to an input of an LTI system, the output would be the same exact function e to the power st, only multiplied by a constant. So it's only a matter of dividing this input into summation of or superposition of e to the power st and computing h of s at s1, s2, and s3, and so on. And this is the key idea behind the Laplace transform, why you are actually using Laplace transform to represent signals in order to make it easier to facilitate dealing with LTI systems. So let's move back to our slide over here. So considering an input signal of the form e to the power st, and we need to find the output y of t. So applying the input x of t to the system, or the system h operating on the input, we will do a convolution as we have learned in the previous chapter, which is integration from minus infinity to positive infinity, h of tau x of t minus tau d tau. Now, x of t is e to the power st, so x of t minus tau is e to the power st minus tau d tau. Now e to the power st is a constant with respect to tau, so we'll move it outside the integration and we'll end up with integration from minus infinity to positive infinity, h of tau e to the negative s tau d tau, which we call h of s, because again it depends on h small, which is the impulse response, and its function of s. Tau will kind of disappear after we integrate and substitute with the limits. So we can write that the output signal y of t will be exactly the same as the input signal e to the power st times h of s. h of s is called a system transfer function, and it's basically the Laplace transform of the impulse response h of t, which is the integration from minus infinity to positive infinity h of t e to the negative st dt. So the action of the system on an input of the form e to the power st is simply multiplication by the system transfer function h of s. And in this case, e to the power st is called an eigenfunction. So e to the power st is an eigenfunction, and h of s, which is the constant by which we multiply e to the power st, it's called the corresponding eigenvalue. So, and given the simplicity of describing the action of the system on an input of this form, because it's really simple to deal with inputs of this form e to the power st, now we seek a representation of any arbitrary signal as a weighted superposition of eigenfunctions e to the power st. So again, this concept is very important. Since it's really simple to deal with inputs of the form e to the power st, we only multiply by h of s. Now, what if we can express any arbitrary signal as a superposition of e to the power st? This will actually simplify the dealings, the interactions with LTI systems. So, The Laplace transform simply goes like this. If we have a continuous time signal x of t and we want to compute its Laplace transform, we will call it x of s. Usually we will use lowercase to represent time domain signals and uppercase to represent s domain representation, x of s. So x of s is simply the integration from minus infinity to positive infinity x of t e to the negative st dt. This is the definition of the Laplace transform, and this equation has come up in the previous derivation when we had h of s. It was equal to the integration of h of t e to the negative st dt. And the inverse Laplace transform is defined using this equation, 1 over 2 pi j integration x of s e to the power st ds. This kind of integration is called a complex integration because we are integrating with respect to a complex variable, which is s. S is a complex variable sigma plus j omega. And there are procedures to evaluate complex integrals which are out of scope for us. So we will actually use different approaches to compute the inverse Laplace transform. So the Laplace transform equation, you have a time domain signal and you want to find x of s, its Laplace domain representation. And the inverse Laplace transform, if you have x of s, now you need to find the corresponding time domain signal. And again, we will not be using this definition. We will actually be using a different approach to find inverse Laplace transform. But even though, let's take a closer look at this equation. Considering that integrations are sort of summations, so this equation is simply saying that x of t, the time domain signal, is represented as a summation of e to the power st. And every e to the power st is weighted, it has a weight, x of s. Compare this interpretation with this example, where we have x of t as a superposition of constants time e to the power st. So simply, the equation of the inverse Laplace transform is saying, it's simply saying that any continuous time signal x of t can be expressed as a summation of, or a superposition of, complex exponentials of the form e to the power st multiplied by constants x of s, again constants with respect to time. So x of s, which is the Laplace transform of x of t, are the weights of the complex exponentials e to the power st. So the previous equation represents the signal x of t as a weighted superposition of complex exponentials e to the power st, and the weights are proportional to x of s. But in practice, we usually do not evaluate this integral directly since it requires techniques of contour integration. So instead, we will determine the inverse Laplace transform by exploiting the one-to-one relationship between x of t and x of s. Basically, we will be building sort of a lookup table. This x of t has this kind of transform, this x of t has this kind of transform, and we will use this table to do the inverse transform, as we're going to see later on. So let's now discuss the convergence of the Laplace transform. And by convergence we mean, given that the definition of the Laplace transform involves an integration going from minus infinity to positive infinity of the function we have e to the power minus st dt, this integration is going from minus infinity to positive infinity, so it might actually converge. In other words, its value might be a finite value, or it might diverge and the value might go to infinity. So let's go back to our whiteboard over here. So the definition of h of s is the integration from minus infinity to positive infinity, h of t e to the negative st. So let's try to replace e to the negative st over here with e to the power sigma plus d omega t. So in this case, h of s will take the form integration from minus infinity to positive infinity, h of t e to the power minus sigma t e to the power minus j omega t dt. And of course, we didn't study Fourier transform, but this equation is simply the Fourier transform. This is the definition of the Fourier transform of a function h of t e to the minus sigma t. So if you want to find the Fourier transform of a function, you do the integration of this function times e to the negative j omega t dt. So the convergence of the Laplace transform is controlled by this function. This function has to be absolutely integrable. That is basically to say that the integration from minus infinity to positive infinity x of t e to the minus sigma t is less than infinity. So if this function x of t e to the minus sigma t is absolutely integrable, this means that the Laplace transform will converge. Otherwise, the Laplace transform will diverge. And as you can see, this integration depends mainly on the function x of t and on the value of sigma over here. That's why the range of sigma for which the Laplace transform converges, in other words, the range of sigma for which this inequality holds, is called the region of convergence. And the region of convergence is an essential part of the Laplace transform. So whenever you compute the Laplace transform, you need to specify the region of convergence, for which part of the sigma values we have a convergent Laplace transform. So please note that the Laplace transform can be seen as the Fourier transform of x of t e to the minus sigma t. As we have seen over here, this expression, this integration is the Fourier transform of this function, h of t e to the minus sigma t. So here we can see a relation between the Laplace transform and the Fourier transform. And of course, while we are at it, let's consider the case if we let sigma to be equal to 0. If we let sigma to be equal to 0, h of s will be h of s is sigma plus j omega, so it will be h of omega simply, right? And this will be equal to integration from minus infinity to positive infinity h of t e to the minus j omega t dt. And now we do not have this term e to the minus sigma t because sigma is equal to 0, so e to the power 0 is 1. And this is simply the definition of the Fourier transform. This is the definition of Fourier transform. So Fourier transform is simply the Laplace transform evaluated for sigma equal to 0. This is a very important thing to note, and let me write it down over here. So if you evaluate the Laplace transform at sigma equal to 0, the Laplace transform evaluated at sigma equal to 0, this will give you the Fourier transform. Okay, and applying this to the system transfer function, so the system transfer function h of s, if it's evaluated at sigma equal to 0, this will give us h of omega, which is called the frequency response of the system. This is called the frequency response of the system. And I'm sure you have here this expression in circuits. And h of s, of course, is the system transfer function. H of s is called the system transfer function. So there is a strong relationship between Laplace transform and Fourier transform. Okay, so Laplace transform is a Fourier transform of x of t e to the minus sigma t. If you put sigma equal to 0, Laplace transform will be actually equal to the Fourier transform. So the Laplace transform exists for signals that do not have Fourier transform, which is a significant advantage gained from using complex exponential representation. How is that? Let's imagine we have this kind of signal x of t, which is a growing exponential. If you try to apply Fourier transform to this signal, you will get infinity. You will not be able to apply Fourier transform for this kind of signal because it's not absolutely integrable. But if it's multiplied by e to the minus sigma t, how can we do that? By computing the Laplace transform. Because computing Laplace transform, you multiply x of t by e to the minus sigma t. So as if computing the Laplace transform is equal to computing the Fourier of x of t times e to the minus sigma t. And now you have a function that you can compute the transform of. And now we can see what values of sigma will give you a finite value, what values of sigma will give you infinite value depending on the region of convergence. We will discuss this in more details in the next few examples. So now we have defined what's Laplace transform and why do we need it, and we have seen that S, the complex frequency variable we have, is a complex variable. It's defined as sigma plus j omega. So sigma over here is the real part, and j omega is the imaginary part, and usually complex variables can be represented in two-dimensional space, as you can see over here, where this is the real axis and this is the imaginary axis. So in general, we will be dealing with the S-plane a lot in this chapter, dealing with the positions of what's called poles and zeros, are going to see in a second. So it's convenient to represent the complex frequency S graphically in terms of a complex plane in a two-dimensional space that we call the S-plane or the S-domain. The horizontal axis represents the real part, sigma, and the vertical axis represents the imaginary part, which is omega. And note that if x of t is absolutely integrable, then we may obtain the Fourier transform from Laplace transform by setting sigma equal to 0. So if you have x of s and you evaluate x of s at sigma equal to 0, this will give you x of j omega or x of omega, which is a Fourier transform of x of t. This is exactly what we have said over here. If we have h of s, which is a system transfer function, we evaluate it at sigma equal to 0, this will give you the frequency response or the Fourier transform of the impulse response. So this simply is saying that if this is the S domain, sigma equals to 0 is basically this imaginary axis, the j omega axis. So setting sigma to be equal to 0 is simply as if we are evaluating the value of x of s only along the imaginary axis, j omega axis. Okay, so in the S-plane, if sigma equal to 0, this corresponds to the imaginary axis. So we say that the Fourier transform is simply the Laplace transform evaluated along the imaginary axis, the j omega axis. The most commonly encountered form of the Laplace transform is the form of a rational function. A rational function is a function that's basically a ratio between two polynomials. That is, x of s will always take the form one polynomial in the numerator over another polynomial in the denominator. The polynomial in the numerator is of order 1, and the polynomial in the denominator is of order n. So if we have a polynomial of order m, we can do factorization and can factorize this polynomial into m first order terms of the form s minus a constant, z, we'll call it z. And the polynomial in the denominator is of order n, so we can factorize this polynomial into n first order terms of the form s minus p. So putting this in mathematical form, if we express the numerator as a multiplication of m terms of the form s minus ck, and this symbol here over here, which is similar to pi, it's basically a multiplication operator, similar to the summation. So summation is adding terms, this notation means it's a product. We're multiplying these terms together. So basically s minus c1 times s minus c2 times s minus c3 up to s minus cm. Since we had an mth order polynomial in the numerator, a polynomial of order m, we can factorize this into m first order terms of this form, s minus ck. And the polynomial in the denominator was of order n, so we can factorize this into a multiplication of n first order terms of the form s minus dk. So s minus d1 times s minus d2 times s minus d3 up to s minus dn. ck are called the zeros of this function. How is that? If you put s equal to c1, so you will get a 0 in the numerator and the whole function will be equal to 0. If you put s equal to c3, the term s minus c3 will become 0 and the whole function becomes a 0. That's why ck, which are the roots of the polynomial in the numerator, are called the zeros of x of s. They are the values of s which makes x of s equal to 0. Whereas dk are called the pools of the function x of s. How's that? If you set s equal to d1, so you will get a 0 in the denominator, which will give you infinity in the total value of the function x of s. So dk, which are the roots of the denominator, are called the pools of x of s. A pool is basically going to infinity, a value that's very high and going to infinity. So x of s having the form of a rational function, a ratio between two polynomials, we can always express the polynomial in the numerator as a multiplication of first order terms, from which you can get the zeros, and the polynomial in the denominator you can always express it as multiplication of first order terms, from which you can get the pools. And it's very common that we need to find the pools and the zeros of any Laplace transform x of s or h of s. We denote the location of zeros in the s-plane by an O and the location of pools by an x, as shown in the figure below. So here we have an x over here, x over here, and x over here. These x's correspond to pools, whereas this O over here, over there, and this O represents a 0. The location of pools and zeros uniquely specifies x of s, because if you know the location of pools and zeros, you can write x of s as a multiplication of s minus the first 0 multiplied by s minus the second 0 multiplied by s minus the third 0, and so on, over s minus the first pool multiplied by s minus the second pool, and so on. And by the way, the number of pools is known as the order of the system. So whenever you hear about a third order system, it simply means that it has 3 pools, or the polynomial in the denominator is of order 3. So our first example today, we have a function x of t of the form e to the power at times u of t. And here a is assumed to take only real values. And we need to find the Laplace transform and the region of convergence and the location of pools and the location of zeros. But before we do that, the example here is calling this signal a causal signal, a causal exponential signal. So it's an exponential signal. It has the form e to the power at. But why is it called a causal signal? If you remember, a causal system is a system whose impulse response is 0 before time t equals 0. So the description of causality is only for systems. Signals cannot be causal. So how is that in the textbook he's calling this signal causal? The idea is that if this signal is the impulse response of an LTI system, this LTI system would be causal, because x of t over here is multiplied by a u of t, so it's basically 0 before t equal to 0. That's why it's considered to be a causal signal. But again, causality is a description of a system rather than a signal. So here what's meant is simply that if this signal becomes the impulse response of an LTI system, it will be a causal signal. So let's try to solve this example together. So now we have x of t, which is equal to e to the power a t times u of t, and a is assumed to be real valued. So let's move to our whiteboard over here, and a is assumed to be real. So in order to find x of s, we'll apply the definition: integration from minus infinity to positive infinity of the function we have, x of t, times e to the minus st dt. X of t in our case is multiplied by unit step u of t, so the integration should start from 0 up to infinity, because from minus infinity up to 0, the u of t part of the function will give us a 0. So it's basically e to the power at times e to the power minus st dt. In order to evaluate this integration, this will be equal to integration from 0 up to infinity. And now let's combine e to the power at and e to the power minus st together. So we will be having e to the power s minus a t dt, and of course we have a negative sign over here. So doing this integration, we will be having 1 over s minus a with a negative sign times e to the minus s minus a t, and now we need to substitute from 0 up to infinity. And now let's start replacing s by sigma plus j omega. So now we will be having minus 1 over s, which is sigma, plus j omega minus a times e to the power minus s, which is sigma, plus j omega minus a times t from 0 up to infinity. So this will be minus 1 over sigma plus j omega minus a times e to the minus sigma minus a t times e to the minus j omega t, and again from 0 up to infinity. So e to the power minus j omega t, using Euler's equation, we know that this term will be cosine plus j sine. It's kind of an oscillating part of the function. But the problem actually here will be with the term e to the minus sigma minus a times t. So if sigma minus a is a positive number, is larger than 0. If sigma minus a is larger than 0, in this case, the exponential we have will be a decaying exponential. So this exponential will be a decaying exponential. If sigma minus a is a positive number, so we will be having e to the minus a positive number times t. It's a decaying exponential. So as t goes to larger values, this exponential will be decaying. And in this case, the Laplace transform x of s will take this form: minus 1 over s minus a. So over here, we have simply combined sigma minus j omega as s one more time. And now, when we substitute with infinity, we will be having e to the power minus infinity, which will give us 0, minus, here we will be having e to the power 0, which is 1. So in this case, the Laplace transform will be equal to 1 over s minus a. So the Laplace transform in this case x of s would be 1 over s minus a. But there was a condition, which is simply sigma minus a larger than 0, or sigma larger than a, and this would be our region of convergence. So the region of convergence, if you remember, are the values of sigma for which x of s takes on finite values. So if sigma is larger than a, this means that sigma minus a is positive, and this means x of s will take this form, x of s minus a. Usually the ROC is kind of drawn in the s domain. This is sigma and this is j omega, and if this is the value of a, so now the region of convergence is simply all the values of sigma which is larger than a. So this will be the region of convergence, and this is a very important result and a rule that we need to learn. If we have a sequence in time that is right-sided, if you look at this sequence in time, this sequence is a right-sided sequence because it's multiplied by a u of t, so it starts at t equals 0 and going up to infinity, so we call it a right-sided sequence or a right-sided signal. So if we have a signal that's right-sided, the region of convergence, as a matter of fact, will also be right-sided. How's that? If you take a look at the region of convergence, it is to the right of the value a, so it's kind of right-sided as well. So again, if you have a right-sided signal, you will get a right-sided ROC. Okay, so what would happen if this condition over here was not satisfied? If sigma minus a is less than 0, it's a negative value. So the negative value will cancel out with this negative sign, and we will be having e to the power of a positive number times t. So whenever t goes to infinity, this term will go to infinity and x of s will diverge. So in the region of convergence over here, if sigma is less than a in this region, the values of x of s will go to infinity and it will diverge. Whereas if sigma is larger than a in this region, we will get a finite values of x of s. So the concept of region of convergence is actually very, very important when you are evaluating the Laplace transform. So moving back over here, as you can see, this is the value of the integration, and we moved on by replacing s by sigma plus j omega, and we concluded that if sigma is larger than a, then this term will go to 0 as t approaches infinity, and x of s will take the form 1 over s minus a whenever sigma is larger than a. Of course, sigma is the real part of s, so we can write as well that the ROC is that the real part of s is larger than a, or sigma is larger than a. So we were asked to find the ROC and the pools. So where are the pools of this function? If you take a closer look at the expression of x of s, we have a first order term in the denominator. So it's basically a rational function, a ratio between a polynomial of 0 order in the numerator and another polynomial of the first order in the denominator. And this polynomial is already factorized as a one term of first order. So it's taking the form s minus a. So a is actually the pool. So we have a pool over here, one pool, and this pool is located at a, at s equal to a. Because if you set s equal to a, you will get 0 in the denominator, which will give you infinity over here, which is a pool. So a pool is a very large value happening. And that's why we have expressed this pool or represented this pool by an x. As we have agreed before, an x will be used to represent a pool, O will be used to represent a 0. Okay, so moving back to our example over here, as you can see, we have a pool located at S equal to A. And again, there is a very important note. The region of convergence starts and ends at pools. So the region of convergence over here starts at this pool. And since there is no other pool, it ends at infinity. The region of convergence usually starts at pools and ends at pools. Okay, so let's move on. This is the region of convergence. So if this is a pool at A, the region of convergence will be kind of right-sided. So again, if you have a right-sided signal, you will get a right-sided sort of region of convergence. Let's move on to our next example over here, which is e to the power at times u of minus t. So it's an exponential function as well, but now it's a left-sided exponential function. U of minus t is a unit step going from minus infinity up to 0 with a value of 1 and 0 otherwise. And this kind of signal might be referred to as a left-sided signal or an anti-causal signal. As you can see over here, it's called an anti-causal signal because it's not causal. For a signal or a system to be causal, the impulse response has to be 0 for t less than 0. So this kind of signal is anti-causal. It's not causal. So, and we need to find the Laplace transform of this signal. So let me write this down. So we have a signal, it's called y of t over here. Y of t is equal to minus e to the power at times u of minus t. And again, we need to find the Laplace transform and the region of convergence. So let's go back to our whiteboard over here. So as you can see, this signal, we can call it a left-sided signal because it's going from minus infinity up to 0. Left-sided signal. So in order to find the Laplace transform, let's apply the definition. So y of s should be the integration from minus infinity up to plus infinity, but now u of minus t will have a value of 0 for any value of t larger than or equal to 0. So the integration will be from minus infinity up to 0 of the function we have, which is e to the power at with a negative sign over here, times e to the minus st dt, which is similar to the one we had in the previous example, except for the limits of the integration are different. So y of s will be equal to minus integration from minus infinity up to 0, and now we will be having e to the power minus s minus a t dt, and this will be minus 1 over s minus a with a negative sign, and e to the power minus s minus a t, and now we need to substitute with the limits e to the minus from minus infinity up to 0. And in this case, again, we'll be replacing s by sigma minus j omega. So y of s will be, of course, this negative sign will cancel out with this negative sign, so we will get 1 over s minus a, and then we will have e to the minus, s is sigma plus j omega, so we'll be having sigma minus a plus j omega t, and now we need to substitute for t at minus infinity and 0. So again, we need to put a condition on sigma minus a. If sigma minus a is less than 0, if it's a negative value, so now we will be having a term of the form e to the minus sigma minus a times t, which is e to the power of a positive value times t. So when t goes to minus infinity, this term will give us 0. So in this case, y of s will be equal to 1 over s minus a, and now substituting with 0, e to the power 0 is 1, minus, substituting with minus infinity given this condition will give us 0, so y of s will take the form of 1 over s minus a, and of course the region of convergence is sigma minus a less than 0 or sigma less than a. So now y of s will be 1 over s minus a, which is exactly the same as the form we found for the previous example, which was a causal sequence or a causal signal. Here we have an anti-causal signal. The difference is in the region of convergence over here. The conditions that need to be satisfied is that sigma minus a is less than 0, which is sigma less than a. And this is the region of convergence. And if we try to draw this region of convergence in the S domain, if this is the S domain over here, this is sigma, and this is j omega, and this is the value of a. So the region of convergence for this Laplace transform would be for sigma less than a. So again, the same observation we had before. When in the previous example we had a right-sided signal, the ROC was kind of right-sided. It was sigma larger than A. In this example, we have a left-sided signal, and the region of convergence is also left-sided, sort of. Okay, so moving back over here, as you can see, we have one pole located at A. So here we have one pole located at S equal to A. So in the S domain over here, we can represent this pole by setting or having an X like this. So again, poles are denoted by X, zeros are denoted by an O. And again, the same observation we did in the previous example, region of convergence starts and ends at poles. So one way of finding the region of convergence is to find the poles and staying away, staying clear of these poles. So moving back over here, we will get y of s is 1 over s minus a, where the region of convergence is the real part of s, which is sigma less than a. And this would be the region of convergence, left part, or sigma less than a. Again, it's a left-sided signal, so we have a left-sided sort of region of convergence. And these kind of observations will help us a lot when we are doing the inverse Laplace transform, as we're going to see later on. So the two previous examples reveal that the Laplace transforms x of s and y of s are of equal value. Both of them had the value 1 over s minus a. Even though the signals in time domain x of t and y of t are completely different. X of t is a right-sided signal, whereas y of t is a left-sided signal. How is that? Because they have different region of convergence. So the region of convergence is an essential part of the Laplace transform. It has to be specified, otherwise we'll be having a problem